In this video, we will start with analog to digital converter. In the previous videos, we tried to understand digital to analog converter where the input was the binary data and you are converting that binary data into an analog voltage. In this video, we will convert an analog voltage into its equivalent binary data. That means analog voltage will be converted into digital data. So that is what is there. Under the heading of analog to digital converter, we will try to understand three circuits: simultaneous type A to D converter, counter ramp type A to D converter, and successive approximation type A to D converter. Each of them is very important with respect to your exam. So we'll start with simultaneous type A to D converter. Make sure that you understand the concept properly. In the notes you will be given the entire write-ups of how the construction is done and how the working of that circuit is done. So whenever this question will be asked, the question will be like, explain simultaneous type A to D converter. So you have to write you have to draw the diagram first, and then you have to write the construction as well as working. Of course that will be provided in the notes which I'll share with you. Now at present you will just try to understand the working of simultaneous type A to D converter. So let us say there is a potential, positive potential, which is applied. I will take a generalized value and then we will take a specific example to understand the working. So let us, a positive supply is applied, and that supply is applied to 4 resistance connected in series. So the potential is applied between ground and a positive value, and there are 4 resistance R. Of course what you can see is the resistance are connected in series, and when the resistance are connected in series, current remains same, voltage divides. So such an arrangement is called as voltage divider arrangement. So the potential at this point, the potential at this point, the potential at this point will depend upon the value of resistance. And in the previous video I have already told you the formula for voltage divider arrangement. What is the formula? Total voltage divided by total resistance multiplied by the resistance across which voltage is taken. So if you want to calculate the voltage at this point, say the value will be, what is the total voltage? Plus VCC. What is the total resistance? 4 resistance connected in series. So R plus R plus R plus R. So the value will be 4R multiplied by, between this point and ground, the value of resistance is R. So R. So if you cut R, the value will be plus VCC by 4. We are actually trying to find out the reference voltage. Okay, plus VCC by 4. What about this point? Think, what will be the potential at this point? Again we have to apply voltage divider arrangement. What is the value? Total voltage is plus VCC, total resistance is 4R multiplied by, between this point and ground you have 2 resistance. So R plus R, 2R. RR gets cancelled. This will be plus VCC by 2. So this is the reference point at this point, plus VCC by 2 in case of voltage level. Now last one at this point, again plus VCC by 4R multiplied by, between this point and ground you have R plus R plus R. So it will be 3R. So RR gets cancelled. It will be plus 3 by 4 of VCC. So this is the reference voltage at different points. This reference voltage is given to a comparator circuit. Comparator circuit. So this is comparator 1, this is comparator 2, this is comparator 3. So there are 3 comparators. Basically this comparator will compare, two voltages, and the output will be either 0 or 1 depending upon the input voltage which has been applied. Of course, as I said, it will be this comparator. What they are going to do, they will be comparing voltages. So what happened is, one input we have already connected, which is nothing but the reference voltage. For the first comparator, the reference voltage is plus VCC by 4. For the second comparator, the reference voltage is plus VCC by 2, and the third comparator, the potential or the reference voltage is plus 3 by 4 of VCC. Basically, what we are trying to do by designing this circuit, we want to convert an analog voltage into its digital equivalent. So the analog voltage which we are going to apply, or for which we want the digital output, that will be forming the other input of the comparator. So one input of all the comparators will be connected together, and it will be connected to V analog, for which we want digital output. So every time you give an input, what happens is this voltage will be compared with the reference voltage, plus 3 by 4 VCC, plus VCC by 2, and plus VCC by 4, and according to the voltage, the comparator's output will be either 1 or it will be 0. And the output of this comparator will be given to a 3-bit encoder. 3-bit encoder, or we say 3:2-bit encoder. 3:2-bit encoder. That means the output will be 2 binary data. And if you just consider this as we have already done 3-bit adder, a circuit which adds 3 binary bits and provides 2 output. Every time you add a binary number, you will get 2 outputs, sum and carry. So we'll make sure that this B is a sum and the A is a carry. So you just have to understand that 3:2-bit encoder will take 3 input, add the 3 binary number, and it will give you as 2-bit as output, sum and carry, which will be the binary equivalent of the analog voltage which we are going to apply. Now, to understand the working, it is very important that how the comparator works. See, the comparator output, it is very important to understand this. Comparator output will be equal to 1. Comparator output will be equal to 1 when V analog is greater than or equal to V reference. V analog is greater than or equal to V reference. That means output of the comparator, as I said, the comparator will be comparing the voltage. So if V analog is greater than equal to plus VCC by 4, whatever be the value, if it is greater than that, the comparator output will be 1. Or if that condition doesn't satisfy, the output of the comparator will be 0. So on the basis of that, we will try to understand the working and try to understand the truth table for simultaneous type A to D converter. So the truth table will be like this. How many comparators we have? C1, C2, C3, and you have A, B, which is your binary output. Let us take an example and try to understand the working, how exactly analog voltage will be converted into its equivalent binary data. Now let us say, instead of positive supply, as I take generalized plus VCC, I'll take now that voltage as 16 volt. So as soon as I take plus VCC as 16 volt, what will be the VCC by 4? 16 by 4, the reference voltage here will be 4 volt. 16 by 2, the reference voltage will be 8 volt. 16 into 3 by 4, that is, the value will be 12 volt. So now the reference voltage has been specified: 4 volt, 8 volt, 12 volt for comparator 1, comparator 2 and comparator 3. Now this comparator will compare the analog voltage with the reference voltage 4 volt, 8 volt and 12 volt. Let us take an example where V analog is 12 volt. V analog is 2 volt. So at each of this place you have 2 volt. As I said, the comparator will compare the voltage and the output will be either 0 or 1 depending upon the input analog voltage. And what is the condition for comparator outputs to become 1? Analog voltage should be greater than or equal to V reference. Now in this, 2 volt is less than 4 volt, 2 volt is less than 8 volt, 2 volt is less than 12 volt. So all the three comparator, this condition is not satisfied. So output of the comparator will be 0, 0, 0. So while writing the truth table, what we will do is instead of writing 0, we will write as low. So output of all the three comparators are low, 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 low. Now this 3:2 bit encoder will add the three inputs, 0 plus 0 plus 0, sum 0, carry 0, sum 0 and carry 0. That means B will be 0 and A will be 0. So this is the number. Now, so when you get the output as 0, 0, what you can say is what should be the analog voltage. Let us take one more example. Suppose if I change this value as 1 volt, what happens? Still 1 volt, here all the inputs will be 1 volt. Still the same condition prevails, the analog voltage is less than the reference voltage, output of all the comparators will be 0, the output A and B will be 0, 0. If I do that as 3, one input of all the comparators become 3, still the same condition prevails, output of all the comparator will be 0 and therefore A and B will be 0. That means the output A and B is 0, 0 for a range of analog voltage, not one single analog voltage, for a range of analog voltage. So 0 to 4, that means we can say it will be ground potential 2 plus VCC5. If the voltage exceeds this, the comparator will become 1. If it has not become 1, that means if it is 0, the voltage has not crossed this limit. What is that limit? Plus VCC/4. So what is the range of voltage? Range of voltage when the binary input is 0, 0 is plus VCC/4. Sorry, it will be 0 volt, that is ground, to plus VCC/4. Let us take one more example. Say the potential here is 6 volt. Now what happens? See, one input of all the comparator will now be 6 volt. So check the condition, comparator 6 volt is greater than the reference voltage, the output of this comparator will become 1. 6 volt less than 8 volt, 0. 6 volt less than 12 volt, 0. So this is the condition which has to be checked. So what will be the output now at this point? C1 is high, C2 is low, C3 is low, and 1 plus 0 plus 0, 1 plus 0 plus 0 will be sum 1 carry 0, sum 1 and carry 0. So B will be 1 and A will be 0, right? So now what you can see is the analog voltage has crossed this limit, but it is yet to cross this point. That means the binary output which we will get, A is 0 and B is 1, the range of voltage will be plus VCC/4 to plus VCC/. Next, because see, what we are trying to say is the range is, because even if I apply 7 volt, the same condition will prevail. Here the output will be 1, here the output will be 0, 0. If I say 5 volts, still here the output is 1, here the output will be 0, 0. So the range of voltage which will be there will be the limit as plus VCC/4 to plus VCC/2. Next, let us take an example as say 9 volt. So what 9 volt? 9 volt will be the one input here. 9 volt compared with 4 volt, the output will be 1. 9 volt compared with 8 volt, again the output of this will be 1, as analog voltage is more than the reference voltage. And 9 volt compared with 12 volt, the output will be 0. So now here the output will be high, high, low. So 1 plus 1 is 10. And 1 plus 1, 10 means sum 0 and carry 1. So now A becomes 1 and B becomes 0. So just imagine, what if I apply 10 volts here? If I apply 10 volts, still the same condition will prevail. If I if I apply 11 volts here, still the same condition will prevail. That means for a range of voltage, now the analog voltage has crossed this and this limit, but it hasn't crossed this limit. So the range of voltage in this point will be plus VCC by 2 to plus 3 by 4 of VCC when the output, binary output, is 1 and 0. And in the say last example which I take, say 14 volts. So 14 volt, if I apply 14, that means output of all the comparator will be 1, as analog voltage is greater than the reference voltage. So the output will be high, high, high. Now 1 plus 1 plus 1, in binary 1 plus 1 is 10, 10 plus 1 is 11. So both A and B are 1. So the output, binary output, we will get as 1 by 4. So now the voltage, analog voltage, has crossed this as well as this limit, and it will be up to plus VCC. So the range of voltage will be plus 3 by 4 of VCC to plus VCC. So this is how you will get for a range of analog voltage, you will get a binary value, and this truth table illustrate how the circuit works. It is called as both simultaneous type A to D converter as well as flash type A to D converter. The only disadvantage related to this circuit is that it doesn't give you digital value for a single analog voltage. It gives you for a range of analog voltage. This is the disadvantage which can be overcome by a circuit called as counter ramp type A to D converter. So that we will see in the next video. Thank you. In the previous video, we tried to understand simultaneous type A to D converter. In that, the disadvantage is the output binary value is not for one single analog voltage. It is for a range of analog voltage. So that disadvantage can be removed by using counter ramp type A to D converter. So when you say counter, yes, of course, the counter which we have studied in chapter number 4, which counts incoming clock pulses. So we will use few circuits and then we will make a circuit which will count, which will be converting an analog voltage, a single analog voltage, into its binary equivalent. So let us start. See this construction part. Again, the question will be for 4 marks. Explain the working of counter ramp type A to D converter. You have to draw the diagram, you have to write the construction and working of that particular circuit. So I will be drawing the diagram and explain you how the circuit has to be constructed, as well as the circuit has to be how the circuit will work. We will see both the things. So the first thing is there is a start pulse, S-T-A-R-T, start pulse. This is where you will press when you want to start a conversion from analog to digital, and this start pulse goes to a mono short, which is monostable multi-vibrator, which is a monostable multi-vibrator. Now monostable multi-vibrator is a circuit which has only one stable state. The output will be continuously 0, and if you give trigger, the output will become 1 for a small duration of time, and again it will be 0. So this is what is called as mono short, which we have already studied in chapter number 5. Flip-flops, counters and shift registers. Monostable, bistable, astable, out of which we will be using mono short, monostable multi-vibrator. So the output of this monostable will become 1 for a short duration of time, and again it will become 0 when you give a start pulse. Now the output of the monostable will be given to, if you remember this symbolic representation, this symbolic representation is for SR flip-flop, where S stands for set and R stands for reset. If you remember, when S is equal to 1, R is equal to 0, trigger is provided to S, and when trigger is provided to it, the output sets, and the output sets means Q will become 1, Q bar will be 0. And if S is 0, R is 1, S is 0, R is 1, then what happens is, when S is 0, R is 1, the trigger is provided to R, and when trigger is provided to R, the flip-flop resets means Q will become 0 and Q bar will be 1. This has to be remembered when you understand the circuit. Output of this flip-flop is connected to AND gate, and output of AND gate is connected to an n-bit binary counter, and to the clock input of n-bit binary counter. The n-bit binary counter's output will give you the digital output, and the output of this n-bit binary counter is given to a D2A converter, which converts the digital output into analog voltage, and this acts as a reference voltage, and it is given to a comparator. The one input of the comparator is the reference voltage, the other input is V analog, and the output of the comparator will drive the reset pin of the flip-flops. Now, as I said, the counter will count, and for counter to count, it will have to be given an incoming clock pulse. So clock pulse is separately provided to one input of AND gate. So if the AND gate is activated, this clock pulse will reach n-bit binary counter. The binary counter counts and it gives the output to D2A converter. D2A converter will convert the digital data into analog and give as reference voltage for the comparator. The comparator will compare the reference voltage with analog voltage, and it will produce the output as 0 and 1 depending upon the analog voltage, and that 0 and 1 will be given to the reset pin of the flip-flop. Now there is one more thing. The start pulse is given to monoshot. It is also given to the reset pin of your counter. That means if the counter resets, that means the count will start from 0 0 0 0. So this is what is done. So the first thing which you have to do is you have to give the analog voltage for which the binary or digital data is required. So V analog, let's say 8 volt. So I will apply 8 volt over here. So now that 8 volt is compared with the reference voltage. What we said is, as soon as you apply start pulse, the monoshot will provide a trigger. The output of the monoshot will go 1 for a small duration of time, and at the same time the flip-flop will reset to 0 0 0 0. It will reset to its initial condition. Let us take, say it is a 4-bit binary counter. So if the count will initially reset to 0 0 0 0, so that count is given to D2A converter. D2A converter will convert the digital data into analog voltage. So 0 0 0 0 will be the reference voltage as 0 volt compared with 8 volt. In this case, output of comparator will be equal to 1 when V reference is greater than equal to V analog voltage, because V analog is fixed, V reference is changing. So V reference, when it is greater than equal to V analog, output of comparator will be 1, otherwise the output of the comparator will be 0. So now at this point what happens is, what is the D2A output? 0 volt, because the count is initial state 0 0 0. So this 0 volt compared with 8 volt, V reference is less than V analog, output of the comparator will be 0, which makes R is equal to 0. And here the monoshot has triggered, so the output of the monoshot has become 1 for a small duration of time, which makes S is equal to 1, R is equal to 0. So when S is equal to 1, R is equal to 0, trigger is provided to S. S stands for set, and if S is triggered, Q will become 1, Q bar will be 0. As Q is 1, this AND gate is enabled, and as this AND gate is enabled, the clock pulses will start reaching the clock input of n bit binary counter, and the working of counter is it has to count the incoming clock pulses. So when the first clock pulse arrives, the count changes to 0 0 0 1, the next higher count, which is given to a D2A converter. Now the D2A converter output reference voltage changes from 0 to 1 volt. 1 volt compared with 8 volt, still V reference is less than V analog. This condition is not satisfied, so output of the comparator will be 0, which makes R equal to 0. Now the mono shot has become 1 only for a short duration time, and after that again it will reset to 0. So this makes S is equal to 0. So now at this point S is 0, R is 0, and when both the inputs are 0 for a flip-flop, the output does not change. That means Q will be still 1, Q bar will be still 0, AND gate is still enabled, clock pulse will reach n bit binary counter. The counter will count the incoming clock pulses. So the next count will be 0 0 1 0. So the D2A output will be now 2 volt. This is the ramp signal, counter ramp signal is generated 2 volt. 2 volt compared with 8 volt, still the output is 0, R 0, S 0, Q remains 1, and gate is enabled. Next clock pulse will reach, which will be 0 0 1 1. Now this will continue till this condition is satisfied. And what is this condition? V reference should be greater than or equal to V analog. So what happens is the count will keep on increasing till the value becomes 1 0 0 0. At this point, what happens is the D2A converter will provide the voltage as 8 volt, and 8 volt compared with 8 volt, what happens is this condition is satisfied. V reference should be greater than equal to analog voltage, so it is equal to analog voltage. So 8 volt compared with 8 volt, the output of the comparator at this point will become 1, and comparator output becomes 1, that means R becomes 1. Now at this point S0 and R1 trigger is given to R. R stands for reset. Reset means Q will be 0 and Q bar will be 1. So what happens is as soon as Q becomes 0, this AND gate is deactivated, disables. The clock pulse will not reach n bit binary counter. The binary counter stops. So at that point, whatever be the digital output, what is the digital output? 1 0 0 0. This is the digital output at that point. That will be the digital equivalent of analog voltage 8 volt. So 8 volt is converted into its equivalent digital value. So 8 volt is converted into its digital value. So similarly, if you take example of 13 volt or 5 volt, for each individual analog input, it will provide a separate digital output. So that is the advantage of counter ramp type A to D converter over simultaneous type A to D converter. I hope you have understood. Thank you. Let us try to understand the disadvantage related to counter ramp type A to D converter. Counter ramp type A to D converter. See, what happens is the initial count was 0 and it has reached 1 0 0 after the 8th clock pulse. This is the 0th clock pulse and this is the 8th clock pulse. So it requires 8 clock pulse to reach to its final value. Suppose one clock pulse, one clock is of 5 seconds. So the answer we got is at the 8th clock pulse, so the time required is 80 seconds. So after giving a start pulse, the time required for the conversion was 40 seconds. Now suppose, and this is for analog voltage 8 volts. Suppose if I apply analog voltage of 13 volts, so the value will be 1101. That means the answer will reach at 13th clock pulse. So when 13 clock pulse, the value will be 65 seconds. Similarly, if I go for 15 as analog voltage, it will take 15 clock pulse. The time will be 75 seconds. So what you can see is as I am increasing the analog voltage, the conversion time increases with that value. The conversion time increases. Slower will be the rate of response. So that is the disadvantage of the circuit. As you keep on increasing the analog voltage, the response time of the circuit decreases. It will be slower to give the final value. So this disadvantage can be overcome by one more circuit called as simultaneous type A to D converter. Successive approximation type A to D converter, which we'll see in the next video. Thank you. The next in line is successive approximation type A to D converter. The disadvantage which we discussed in counter ramp type A to D converter was the conversion time increases with the analog voltage. That means when you keep on increasing the analog voltage, the conversion time or the response time of the circuit decreases. It takes longer time to convert the same analog voltage into digital value. So that disadvantage is removed by successive approximation type A to D converter. If you remember, in counter ramp type A to D converter, every time we press a start pulse, the counter will reset to 0 0 0 0. That means it will start counting always from 0, even if it is for 8 volt, 13 volt or 15 volt, it will start counting from 0 0 0. Therefore the conversion time is keep on increasing if the analog voltage is increases. So what we do in successive approximation type A to D converter, let us try to understand the working with a small tree diagram. This is also very important, and this has to be written or drawn in the exam whenever the question is asked. What we do is we start the count from 1 0 0 0. So instead of starting the count from 0 0 0 0, we start the count from 1 0 0 0, and instead of counting, we just decide to whether to keep this 1 or not. Of course, comparing this voltage, of course this digital value will be converted into an analog voltage. That analog voltage will be compared with the this digital value will be converted into reference voltage. Reference voltage will be compared with the analog voltage, and then on the basis of this comparison we will decide whether to keep this 1 or not. So of course every time there will be two conditions which will prevail. This is at the first clock pulse. First clock pulse, what happens is, either what you will do is you will keep the 1 as it is. You have to keep the 1 as it is, add one more 1 to the next lower place if the count is less. We are comparing that value with the analog voltage. If the value is less, we have to increase the count. So what I have to done is keep the 1 as it is, add one more 1 to the next lower place. We will add 1. Suppose if this count is more than the analog voltage, we have to decrease the count. So we have to remove this one and transfer it to the next lower place. So the count becomes 0 1 0 0. So at the end of the first clock pulse, we have made decision on MSB whether to keep that 1 as it is or we have to remove that 1 in that place. Next, in the second clock pulse, we will make again a decision. Either we will go upward or we will go downward depending upon the analog voltage. Again the same condition will prevail here also. Now we will make the decision on the second pulse, second bit, whether to keep that 1 as it is or we have to remove that 1 into the or transfer it to the next lower place. So if you have to keep that 1 as it is, you have to add one more 1 to the next lower place, 1 1 1 0, and if you have to remove that 1, transfer it to the next lower place, the value will become 1. This 1 will be transferred over to the next place, 0 1 0. So this is the condition. Similarly here, if this 1 has to be kept as it, keep the 1 as it is, add one more 1 to the next lower place, 0 1 1 0, remove the 1 and transfer it to the next lower place. So this is what we will do in the second clock pulse. Next, third clock pulse. Keep the 1 as it is, add one more 1 to the next lower place. Now we are talking about the third bit. Third bit पे काम करेंगे, तो उस टाइम पे 1 1 1 1 नीचे आओगे तो remove the 1 and transfer it to the next lower place, 1 1 0 1. ऊपर गए 1 0 1 1, नीचे आएंगे 1 0 0 1. ऊपर गए 0 1 1 1, नीचे आएंगे 0 1 0 1. Next 0 0 1 1 0 0 0 1. So this is at the end of the third clock pulse, and at the end of the fourth clock pulse you will get the result. See, remove the if you have to keep that 1 as it is, what you have to do is keep the 1 as it is, add one more 1 to the next lower place. There is no next one more place, so we have to keep the 1 as it is, 1 1 1 1. The condition remains the same. Then when you go down, remove the 1 and transfer it to the next lower place. Of course there is no lower place, but you have to remove that 1, so it will be 1 1 1 0. Similarly, keep the 1 as it is, remove the 1. Now we are talking about the fourth bit. So 1 0 1 1 1 0 1 0, then 1 0 0 1 1 0 0 0. Keep the 1 as it is, remove the 1. 0 1 0 1 0 1 0 0 0 0 1 1 0 0 1 0 0 0 0 1 0 0 0 0. So at the end of the fourth clock pulse, what you can see is we have all the binary in data from 1 1 1 1 to 0 0 0 0. That means by reaching up to reaching the fourth clock pulse, we will get the answer for 4-bit binary counter. So the whatever be the value of from 0 to 15, the how many counts it will take? It will take only 4 clock pulse. That means if each clock pulse is of 5 seconds, it will take only 20 seconds. So now let us try to understand the circuit diagram for successive approximation type A to D converter. Let us try to understand the logic circuit of successive approximation type A to D converter. So the first circuit is, we call it as logic circuit. This circuit will decide whether to keep that one as it is or you have to transfer that one to the next lower place. The output of this is given to a ring counter, RINGCOUNTER, ring counter, which we have studied in chapter number 5 under the heading of counters. And the output of this ring counter will drive the n-bit binary counter, n-bit binary counter. The output of this n-bit binary counter will give you the digital input, digital output. The output of n-bit binary counter is given to a D2A converter. The output of D2A converter will generate a reference voltage which will be given to a comparator, and one input of this comparator will be V analog. The output of this comparator will compare the two voltages and it will produce the output as either 0 or 1, and the logic circuit will work accordingly. So the logic circuit will provide signal to ring counter as well as n-bit binary counter. So as I said, this circuit will start the counting from 1 0 0 0. Now there are two conditions for this circuit to work. We have to check every time the digital output changes, we have to check these two conditions. When V reference is greater than V analog, we say remove the 1 and transfer it to next lower place. And second, when V reference is less than or equal to V analog, keep the 1 as it is and add one more 1 at next lower place. So these two conditions has to be verified every time. Let us take an analog voltage of 13 volt. If you remember, counter ramp type will take 13 clock pulse to reach this answer 13 volt. So it will take say if one clock pulse is of 5 seconds, it will take 13 multiplied by 5, that is 65 seconds to convert. Now see the same thing what happens in this successive approximation type A to D converter. Before going to that, let us try to understand how the ring counter works. See, the ring counter is like this: 1 0 0 0. With the next clock pulse, this 1 will be transferred over, this 0 will be transferred over, 0 1 0 0, next 0 0 1 0, next 0 0 0 1. That means this ring counter will indicate at which bit we are counting, or to which bit we are working. First clock pulse, we are working on the first bit, second bit, third bit, fourth bit with each applied clock pulse. That is what the ring counter will indicate to the n-bit binary counter, and logic circuit will decide whether to keep that one as it is or not. So now let's say the digital output initially start with the tree diagram which we have explained. They start with 1 0 0 0. So what is the reference voltage? Reference voltage will be 8 volt. 1 0 0 0 converted into analog voltage. So 8 volt. 8 volt compared with 13 volt. What is the condition? Reference voltage is less than the analog voltage. Which of the two condition will prevail? The second one. V reference is less than V analog. So what it has to be done? Keep the one as it is and add one more 1 at the next lower place. The comparator will provide either 0 or 1, and the logic circuit will understand, it will keep the one as it is and add one more 1 to the next lower place. So the next value will be 1 0 0 0, 1 1 0 0. So what will be the reference voltage now? What is 1 1 0 0 now? 12 volt. 12 volt compared with 13 volt. Still the second condition prevail at the second clock pulse. That means reference voltage is less than analog voltage. Again the output will be either 0 1 1, which will make logic circuit to explain n-bit binary counter that you have to keep the one as it is, add one more 1 to the next lower place. So the value will be 1 1 1 0. So the analog voltage of D2A converter will be 14 volt. 1 1 1 0, 14 volt. 14 volt compared with 13 volt. Now the first condition prevails when V reference is greater than V analog. What has to be done? Remove the 1 and transfer it to the next lower place. So you have to remove the 1 and transfer it to the next lower place. 1 1, this 1 has to be removed and it is to be transferred to the next lower place. So at this point the reference voltage becomes 13 volt. Now 13 volt compared with 13 volt, which of the two condition prevails? The second one, when V reference is equal to V analog. Keep the one as it is and add one more 1 at the next lower place. So the value will be 1 1 0 1. This is the value. So how many clock pulse will be required? 0 1 2 3 4. So at the fourth clock pulse we will reach the answer. So 4 multiplied by say a clock cycle of 5 seconds. So 4 multiplied by 20 seconds. So when we started, we discussed that if the same analog voltage is applied to the counter ramp type A to D converter, it would have taken 65 seconds, and in successive approximation type A to D converter, it takes only 20 seconds. So it is much faster as compared to counter ramp type A to D converter. So this is how successive approximation type A to D converter works, and I hope you have understood the working of the circuit. Thank you.